Hi there, this is the third part of the development of a power monitor. If you have missed the previous parts, I put links in the description of this video. In line with the plan at the end of part 2, I managed to move the shunt resistor away from the INA board to be able to add an input filter and protection, design a menu system and write the software for it, look at enclosures and the power supply, and blow up the INA 219 chip and release its magic smoke. Wait, what? That part wasn't planned at all. Oh well, accidents happen. More about that one later, but it's the reason that this video took much longer than planned. The Texas Instruments datasheet recommends adding an input filter to the INA 219 because currents are often quite noisy and this can have strange effects on the ADC. This may be less of an issue when discharging batteries, but think of motors or other applications where you want to measure fast changing currents. I'm particularly interested in measuring smart chargers that pulse batteries to cram more charge in faster. Those measurements are probably quite noisy, so I decided to add a filter. You see, the recommended configuration consists of two 10-ohm resistors and a ceramic capacitor. A second warning on the bus voltages stressed in the datasheet is never to go negative or exceed the 26 volts maximum against ground. This can easily happen, for example through negative kickback if the load has some inductive component and the supply power is suddenly removed. The datasheet recommends clamping the input voltages using transient protection devices. There then is the input section of the current schematics. You recognize the recommended filter from the datasheet. There are two additional transient protection diodes that clamp the inputs to save voltages. I wanted to allow as high voltage as possible and therefore I picked the ICTE18. From its datasheet you can see that it will not kick in until about 21 volts has been reached and clamps the input to between 24 and 25 volts. Very short high voltage transient spikes from inductive loads will be absorbed by the 10 ohm resistors, but they are only quarter watt types and can't handle the current if someone applies negative voltage or more than 21 volts at the input. In this case, the diodes will act as direct short circuit to ground. For this reason I added a fuse that will break the current, hopefully before the resistors or diodes get damaged. This fuse should be very small because normally there's hardly any current flowing through this connection. I use a 100 mA fuse at the moment. If you're not too familiar with these Z diodes for transient protection, they are absolutely massive. Here's a familiar 1N4148 signal diode. A commonly used rectifier diode 1N406 is big compared to the 1N4848. But the transsorb, as these diodes are known, even dwarfs the 1N406. To see how these transorbs work, the red meter shows the voltage across the diode in reverse polarity mode, while the blue meter shows the current in milliamps. When I ramp up the voltage, no current flows until we get to just over 21 volts, after which it increases dramatically. You can't test the clamping that way because the current would be destroying the diode if applied for more than a few milliseconds. To test the clamping, I put the diode in series with a 10K resistor to limit the current to safe levels, but that means I now have to apply much higher test voltages. In this setup, the red meter shows the voltage across the diode as before, but the blue meter shows the applied total voltage. At 160 volts, about 1.4 milliamps, the diode clamps to about 22 volts. The higher clamp voltage listed in the datasheet are because of much higher peak currents. I want to briefly go back to the wiring diagram to explain the rest of the input circuitry. The number of input terminals may look a little confusing, but I designed this unit to have maximum versatility. Normally, the two red terminals are connected by a removable link and the supply side connection goes in either one. The other end is either the yellow terminal, if I don't use the relay, or the white one that goes through the relay. Ground always goes to the black terminal. This arrangement allows me to use different shunts if I want to measure higher currents. For example, I already have a 5 milliohm shunt. To use it instead of the internal 0.1 ohm shunt, I remove the link between the two red terminals and connect the external shunt between the top red one and the yellow terminal. Of course, the software must allow selecting different shunts so the measurements are correct. The removable link is maybe a little bit cumbersome, but replacing it with a switch would be problematic. You see, you just can't switch a shunt on and off, because even good switches have contact on resistance in the milliohm range and thus in the same magnitude as a shunt resistor. And this unknown and unsteady on resistance would be in the current measurement loop and therefore cause significant errors. Replacing the link with a switch is possible, provided you always remember to connect on the lower red terminal when using the internal shunt. In that case, only the INA sense connection goes through the switch, and that is uncritical. But if you ever forget and connect the load to the upper terminal instead, you either fry the switch or cause significant errors. In the end, I decided I'd rather not use a switch and use a simple link that can be made as massive as I want. Finally, the reason for having both the yellow and white terminals is that the relay contacts are only good for about 10 amps max. So for measuring higher currents with an external shunt, the yellow terminal must be used. The relay contacts, by the way, are outside the current measurement loop, so the on resistance of maximum 30 milliohms does not influence the current readings, but will cause a small drop between the voltage measured by the INA 219 on the yellow terminal and the white terminal. To minimize losses, all current carrying wires need to be as thick as possible. Onto the software. Mostly the display will show the run menu, which looks like this. The top line always shows voltage and current, and whether you are using auto range or manual range, and what shunt voltage is currently in use. You will notice that to save space and display numbers with optimal resolution, I had to resort to define a few characters myself for the unit, like here for the milliamps or the milliwatts. Luckily, the LCD display allows you to make up to 8 user-defined characters. The second display line is split in 2 identical spaces. I call them left and right, and I can show one of 15 possible fields in each of the spaces. In this example, left shows the capacity and right shows the energy field, but nothing would stop you from displaying the same field in both positions. Buttons 1 to 4 from the previous version have been renamed Previous, Select, Next and Back. All fields are continuously updated, even if not shown, and short presses on the Previous and Next buttons cycle through the different field options. You can see that I added the capability to change between auto and manual range directly from the run menu, because that's convenient when calibrating, for example, for a different shunt. There is an experimental manual recording mode which allows me to add a line with the current data to the recording file every time I press the select key in the run menu. Otherwise, no data is written to the file, even though recording is technically on. This is quite useful because it captures only the data I'm really interested in, instead of having to find it in the thousands of lines produced by regular recordings. The status field, which is one of the options you can select for display, looks like this. The most left position indicates if recording is going on or not. The next character is either an L or an S, depending on whether the volts displayed are measured from the load side or supply side. A quick explanation on the load side and supply side. The INA 219 measures volts always on the VN- pin, which is termed the load side and goes to the yellow terminal. For example, if I use it to measure a charger charging a battery, then I'm probably interested to see the true battery voltage, and so load side measurement is okay. If on the other side I have a configuration like this, I'm maybe more interested in the supply side voltage, and the setup menu allows this option. All that really happens in that case is that my software adds the load side voltage plus the shunt voltage to calculate the supply side voltage. It also uses this sum and the current to calculate the power instead of using the power value provided by the INA chip, because of course this is based on the load side voltage only. It's really a matter of convenience, because nothing stops you to use a circuit like this, in which the yellow terminal or load side has a higher voltage than the red terminal or supply side. The only effect is that the current shown is negative, and therefore all power, capacity and energy values are also negative. The rest of the status is made of the limit tests. The software allows to set high and low limits on voltage and current, and high only or maximum on runtime, capacity and energy. The status shows what limits are active. In this case, there's only a high voltage limit enabled. Every measurement is continuously checked against all enabled limits, and if any one is exceeded, the relay deactivates and the corresponding status symbol blinks. If the value goes back into the limit, the symbol stops blinking, but the relay will stay deactivated until it's manually rearmed. A quick look at the rest of the menu structure without going into any details. There are 3 levels: main, setup and limits, with some submenus underneath. Those submenus allow you to select something, or to turn it on and off, or edit something, or just show values of the present settings. The main has a run menu, which we already discussed. Limits and setup go to the corresponding submenus, and off goes to shut down. Recording turns the recording in comma separated values or CSV format on or off. The recording file name is made out of the current date and time, so there is no danger of accidentally overriding a previous recording. The relay option allows you to turn the relay on or off. Turning it on rearms the limit test, so if any of the limits are still exceeded, the relay will not turn on at all or immediately turn off again. The setup menu allows looking at the current setting using the show option, resetting to defaults, selecting the load or supply side voltage, changing the options for the recording, or selecting a different shunt resistor. All setup changes are automatically saved and restored for the next time. The limits menu allows setting and enabling of limits. Check for voltages, current, time, capacity and energy. Values and enabling disabling are 2 separate functions, so you can have limit values defined numerically but choose not to enable them for the present run. I have done it this way because editing numbers with the up, down, left, right cursor keys is a bit slow, so you don't want to have to zero a carefully entered number just not to check for it at the current run, and it allows 0 as a valid limit value. For similar reasons, mainly to preserve limit settings you want to reuse occasionally, limit data is not auto-saved, only auto-loaded at start. The save function allows to override the stored values with the present setting. The clear clears them, and the load function reloads the last stored values from disk. Here's a simplified look at how the software works. From one file of about 250 lines in the previous version, the software has grown to more than tenfold, about 2,600 lines over 4 separate modules shown as blue boxes and 8 classes shown in yellow. This diagram uses swim lanes with time going from top to bottom. Everything is driven by the loop executed 10 times per second in the main program, PowerMon. It starts with fetching new data from the INA219 object, containing volts, amps, power, shunt voltage and overflow. This record is passed to the measure object, which does all the calculations, statistics and limits check. If a limit was reached, the relay is deactivated. Next, the loop gets any new button events. If the run menu is currently selected, processing of the button menus is handled within the display. Fetching and displaying data from measure directly, otherwise the handling of other menus is done directly in PowerMon. Finally, PowerMon is calling recording and repeats for another loop unless off was selected, in which case it initiates a cleanup and shutdown. The one important thing to realize in understanding the code is that none of the functions called by PowerMon can wait for anything, be it user input or measurement data. The only waiting is done within the main program loop and automatically adjusted for exactly 10 loops per second. This means, for example, that menu handlers or number editors are coded in such a way to be called by the main program, handle any keyboard events if there are any, and then immediately exit with either a pending or finished state. If it was a pending state, the handler will be called again in the next loop to pick up and continue, or wherever the menu editing was left during the previous call. With all that out of the way, on to the build. To implement the input filter and protection discussed earlier, the onboard shunt resistor on the Adafruit INA board has to go. I found the best way to do this is with two soldering irons heating both ends of the resistor simultaneously, which allows you to slide it off very easily. I spent quite some time considering how to mount and wire up all things together. In the end, I decided on a backplane, which you see here. It plugs into the LCD panel like so. And the Raspberry Pi Zero goes here. The INA 219 plugs into the side. And for the buttons, I decided to go with a ready-made 4-button membrane keypad unit from eBay, which has a connector that also plugs underneath into the backplane. This makes for a very neat and self-contained assembly, and all the messy interconnection wiring can be done very compactly on the backplane. The backplane wiring is exactly like the breadboard wiring used in the earlier parts, except I added a decoupling capacitor pair of 10 microfarad and 0.1 microfarad for the INA chip, following a recommendation in the datasheet. I did this much later, which is why they are not visible in some of the earlier shots. You can see where the Raspberry Pi, the LCD and the INA 219 plug into the backplane. The keyboard connector is here. Note that the VIN plus and minus connections of the INA 219 to the backplane are not used. I decided it would be less hassle to reinstall the terminal block on the INA 219 board for that connection instead of routing it all the way through the backplane. Here is the backplane all wired up, and as you can see, it's quite possible to operate the unit this way, powered via the Raspberry Pi USB port. The INA input circuitry was on an external breadboard, and of course neither the relay or the indicator LEDs are connected. This unit could be fitted into a very compact housing, but I have already bought a larger one which has a design I liked and used before. The housing consists of two U-shaped shells and separate front and back panels that just slide into grooves on the main parts. This shot shows the front and back panels already cut and drilled. The housing also includes a foldable handle that can serve to prop the unit up or completely folds back underneath. The screws fix the feet to the unit and go all the way through to the lid. I like the fact that these screws go into proper metal inserts at the top and not self-tappers. When I got the unit from eBay, I failed to notice that there was a molding problem on the back panel until it was too late. They must have run out of plastic in the factory, but it's not too big a deal as the grooves will cover most of the missing edge. I decided to print covers for the front and rear panels on paper and laminate them. For the front, this has the benefit of creating a clear window protecting the LCD panel, and the button area is more resistant to touch. For the rear, adding a laminated cover isn't necessary, but I decided to do it anyway to cover the missing edge I showed earlier. The LCD panel will be mounted on standoffs using nylon screws glued to the front panel. Here you see a piece of scrap from one of the panel cutouts with 3 screws using different types of glue to see which one works best for this job. After several hours, the results are in. This one is a complete failure. This is a little better, but the screw can still be moved and broken off with little effort. But the third sample is rock solid. It turns out that this superglue is perfect for fixing these screws onto the plastic of this housing. And these are the actual LCD panel standoffs mounted on the inside of the front panel using the same type of superglue. With the LCD inserted, it looks like this. It turned out to look quite nice and fairly easy to do. You will have noticed the slot underneath the panel cutout. This is for the flat ribbon cable of the membrane keypad. The keypad will be fixed on the outside of the front panel and the connector will plug into the backplane on the inside. My idea is that the actual keypad will be covered under the laminated front panel right under the 4 rectangles with my custom key labels. Time to mount the keypad, starting by peeling off the cover of the adhesive backing. This is what the back looks with the adhesive side fully uncovered. It's quite interesting to see how these keypads actually are made. The keypad is now firmly fixed onto the front panel. This is it. I doubt you could ever remove it again without completely damaging it. The rest of the front panel items populated. I made a small measurement error for the overload LED that I could correct with another laminate, but in the end I decided to live with it. The rear panel with a USB B to A pass-through connector I still had and an IAC C14 power inlet with integrated switch and fuse, both of which I have not yet inserted. Speaking of fuse, it's time to address the accident. Of course, I do not have any video footage from the accident, so I'm using this graphic to show what actually happened. While videoing the wiring of the housing, I removed the INA 219 board temporarily to get better views of the relay wiring, which is close by. Afterwards, when I plugged it back in, I accidentally moved it by 1 position downwards relative to the backplane connector. The connector is not keyed, and so the board fits with the wrong position, no problem. When I reapplied power, I noticed that the software crashed because it could not find the INA chip on the bus. There was also the unmistakable smell of way too hot electronics. After killing the power, I noticed that the INA board was very hot and it was in the wrong position. Its VCC pin hung free outside the connector. Instead, the 5 volts from the backplane went to its ground pin and ground was connected to SCL. Amazingly, nothing else was damaged, but the INA 219 chip never recovered after I plugged the board in the correct way. There was no alternative than to remove the fried chip, which I did using my hot air rework station. Then I ordered a replacement from RS Components. After a couple of days, a padded envelope containing an anti-static bag with a tiny speck of a chip inside arrived, and after lots of foul language and many anxious moments, including one where I had accidentally dropped the tiny chip on the floor and spent minutes trying to find it without stepping on it, I finally had the new chip back on board and working. I don't want to go through this again. and so I thought about ways to make this connection safer, and there's actually quite a simple way. By adding two plastic screws left and right into the mounting holes on the INA board, the board will now only fit if it's inserted correctly into the backplane. Here's the video of the front panel wiring and relay that indirectly caused the INA meltdown. It's important to keep the wires to the relay switch contacts as thick and short as possible because the full load current of several amps will go through them. For this reason, the relay is mounted directly on the front panel with a little piece of wood using a cable tie. This is a bit of an overkill because the thick solid copper wires hold it already firmly in place. You can also see the 0.1 ohm shunt, which is one of the usual ones found in multimeters. It is rated to be 5 watts and 1% tolerance. An alternative is to use the resistor from the INA 219 board on a piece of stripboard PCB with extra leads soldered along the stripboard trays to carry the current. The remaining circuitry is handled by this board, which also carries a little 5-volt switch mode power supply. The other components are the INA input filter and protection, the relay driver, and the LED connections. The 4-pin connection to the backplane is here, and the connection to the terminals on the INA boards are these two wires. You will notice there are now 3 LEDs. Besides the overload and relay indicators, the third LED is simply hooked up to +5 volts. I found that such an indicator is needed because the LCD and the other displays are dark when the Raspberry Pi is still booting or has been shut down, and you can't tell if power has been or is still applied. This is how the board looks in practice. The power supply is not very critical and you can use whatever is available, even a scavenged module from a USB wall adapter if you like. Alternatively, you can leave it out and always power the unit from a USB connection. The fuse, by the way, is the one for the INA 219 input protection and not for the power supply module. This one has its own soldered-in fuse on board, but there is of course another one in the IAC connector and a third one in the standard UK power plug. The board fits neatly in the housing, fixed with 2 self-tapping screws on conveniently located studs on the floor. You can also see that I added 2 additional supports to hold the Raspberry Pi so that not everything is hanging off the LCD display. The fully assembled unit. For convenience, the USB connection is actually an existing small micro USB cable out of my large collection of USB cables. Its Type A connector plugs into the back of the USB pass-through connector of the rear panel, and the micro USB end goes into one of the 2 ports on the Raspberry Pi. The Raspberry Pi remains easily accessible, for example, to take out the SD cards or even to temporarily plug in an HDMI monitor. The complete schematic diagram looks like this and is available on my GitHub page together with the software. The transistor is an overkill, but the original relay drew too much current for the smaller BC107 that I have lots of in my parts bin, so I used a more beefier BD139 also from existing stock. Later I found this inexpensive Omron relay that needed far less current and I used that instead, but I left the transistor in place because one possible future change is to add a new connector on the back to allow driving an external relay if the switch current is too much for the internal one. Time to finally close the box and put in those 4 long screws to secure it. Just time for a quick demonstration. The power supply on the top connects through the unit to a 10 ohm resistor as load. I leave the run display and select limits, followed by show. You can see there's a high volt limit for 14.2 volts. The other limits are all 0 and disabled. Going back to the run display. Apart from voltage and current, the run display shows watts and runtime. The A on the upper left means auto range is on, the white LED shows that the relay is active. Selecting the right field with a long press and scrolling through the options to find the status. We can see that the high volt limit is enabled. I'm now increasing the voltage. The difference in voltage between the power supply and the power mon are due to voltage drops, and as the L in the status shows, power mon is currently configured to measure the voltage over the load, not the supply. There, the relay triggered. I was a bit hasty in cranking up the voltage, so we overshot the 14.2 volt limit somewhat. You can see the high volt status is blinking. Let's try to rearm the relay using the relay option in the main menu. It momentarily engages but is immediately triggered again because the unit keeps monitoring in the background. I need to reduce the voltage first below the threshold. Now it works and we can go back into the Run menu. Finally, a quick word on accuracy. This diagram shows the result of two preliminary test runs. The top one shows the error in % of the voltage readout and is quite similar to the one in the last video. I since gave it some thought, and the steep error increase at low voltages is entirely explainable. You see, the least significant bit causes a fixed uncertainty of say 8 millivolts for a 12-bit ADC measuring 32 volts. The weight of this uncertainty in the error percentage calculation increases the lower the voltage gets. So for up to 8 millivolts input you have 100% error. For 80 millivolts, 10%, 800 millivolts, 1%, and so on. This effect adds, of course, on top of the basic accuracy of the chip itself. In practice, this means the readout at low voltages is about 20 millivolts off, so 0.98 volts instead of 1 volt. This may be fixable by a software calibration. The INA219 chip itself has no provision for calibrating bus volt readings. The current graph below covers a large range from 30 milliamps all the way to 3.1 amps or so. The error looks generally acceptable. The large spike happened at 600 milliamps when I had to switch the BM235 multimeter, which I used for comparison, from the milliamps to the amp range. I'm not sure what went wrong at that moment, and I will try to repeat the test. In general, the spikiness is caused by uncertainty of the least significant bit. This video had a lot of ground to cover and fell quite a bit short on demos and usage. It will be the job of the next part, which will also expand on accuracy, whether calibration is needed and how to do it, and what to look out for if you decide to have a go at building it. I hope you found this useful and feel free to leave comments. If you haven't done so already, consider subscribing so you don't miss out the next parts. Thanks for watching.